This video is a part of lecture 2, and that's the video which will address the problem in chapter 1 of lecture notes on page 5. The problem there is about finding the sum of every third binomial coefficient, where n is the number which is multiple of 6. Alright, so first what we will do, we will look at the binomial expansion, or just arbitrary binomial expansion of two numbers a plus b to the power n. We know that this expansion, if you use binomial formula, this expansion will be like so: cn0 a to the power n, cn1 a to the power n take 1 b, cn2 n a to the power n take 2 b square. I also put for you the fourth term in the expansion. This expansion goes all the way until the nth term. That's what these multiple dots symbolize. Also here I put here for you the sigma notation for the same expansion. Right. Now if you take this expansion and if you substitute identities in the position of a and b, something like this, you will end up with a very nice simple expression like so. Well, obviously if your a is identity here, just c and 0 left. If a and b are identities in the position of this term, of course you also end up with just the binomial coefficient. The same story goes here, the same story goes for the cn3. This a to the power n take 3 and this b to the power cube is identities. This goes on for n terms. In the sigma notation this will look something like this: sum of k from 0 to n, c and k, and that's what you end up with. If you look at this closely, you will realize right away that basically here in this expression, you have just the sum of all binomial coefficients, but on the right hand side this is just 2 to the power n. This is actually a very nice observation, that the sum of the binomial coefficients is nothing else but 2 to the power n. However, this problem takes it to the next level, because here we have to look at the sum of the binomial coefficients, not all of them, but every third of them. Right. Now, interestingly enough, complex numbers play a very interesting role in this problem, and you will see this very soon. What we do is this: we take this special complex number, -1/2 plus √3 onto I. We found this complex number in the previous problem, and in previous problem we realized that this is basically the root of unity. So if you cube this number, it will be 1. Something else I'd like to realize is that if you square this number, there are two ways how you can square this number. One of them is just the pure algebraic form of multiplication operation, which we discussed in lecture 1. If you can do it this way. Also, you can square this number by using the exponential form of the complex numbers. This is something we're going to discuss a bit later. But no matter which way you do it, and I'll leave these details for you to discover independently. That's why I put the dots here. No matter which way you do it, you will realize the result will be this one: -1/2 take √3 onto I. This is just a pure arithmetic statement. Like I said, I just leave it for you to check. Now, what I will do now, I'll take this number omega, and I'll use this number in my binomial expansion. Look at this. I'll take my binomial expansion, my original general form of binomial expansion like this, and I'll substitute 1 for a and omega for b. This is easy. Let's just do the expansion. The first term is just the same as before, Cn0. The second term is Cn1 omega. Omega went for B in this formula. The third term, Cn2 omega square. Omega went for B square in here. The third one obviously will be Cn3 omega cube. And you go on in this way. And I can also give here the sigma version of this expansion. Sum of all indices k from 0 to n, Cnk omega k. Now I also would like to consider the binomial expansion where I take omega square for b. This is almost identical to the one we just did. Again, the first term in the expansion Cn0, the next term in the expansion C1 omega square. So this omega square is just this b in this expansion. Next one will be omega to the power 4, and this omega to the power 4, this is the reflection of this b square. Next one, which shows up in line, it's omega to the power 6. You have many more of such terms, and you also have the sigma version of this, like so. It's a sum of indices from k to n of c and k omega 2 to the power k. Right. At this point you might start wondering why we did all of these lengthy, laborious expansions. The answer will transpire very shortly. To see this answer, what I will suggest, we'll just look at these omega numbers, powers of omega number, more closely, and that's what I suggest. Well, that's what I suggest we do. Let's just do it here. Look, let me just introduce this special number, z equal omega to the power k, right? Where k is some positive integer. K is some positive integer. What we see right away is that if you take your z to the cube, then obviously if you substitute omega to the power k for z, you'll end up with something like this. Now you know you can interchange the way you apply your powers to numbers, so we can interchange. And we know, well, here omega cube is just identity, which means that this is identity to power k, and we know that this is just 1. In other words, look at this, z to the cube is just 1. So z to the cube, z in fact, is a solution to this equation, or rather, this equation. That's just a fact. This is just a factorized version of this left-hand side. Now, if I substitute back what omega was, and if I substitute now what my z was, here it is. If I substitute now this into my factorization, so I will end up with this. And now I can analyze this expression. So we got two brackets, which we factor together, and we end up with 0, which means either of them is 0. So we have either omega to the power k equal 1, or we have the second bracket, which is omega to the power 2k plus omega k plus 1 equals 0. Sorry. Let's just first look closely at the first one. Let's just first look closely at this relation. I claim that this is equivalent to just k being multiple of 3. Why it is so? This is because, let me give you some notes about that. Just imagine, let's take any k. So any k obviously admits the representation like this. This is a partial division theorem. So if I divide k by 3 partially, then I have my partial quotient, which is q, and I have my remainder, which takes only these 3 possible values, 0, 1, and 2. Now, if I take now my omega to the power k, and if I now substitute this partial fraction, a partial division expression for k, then I will have something like this. If I could quickly use the properties of powers, then that's how it can be transformed, right? So this combined degree 3q plus r got split over this factor and over this factor. And we again recall right away that the omega cube was 1, so the first bracket here is just 1, and the whole thing just ends up to be omega to the power r, which means that the omega to the power k equal 1 equivalent to omega to the power r equal 1. But r, remember, r was just a remainder of partial division of number k by 3. And so this r is either 0, this r is either 0, 1, and 2. And out of these 3 values, or out of these 3 powers, only 0 delivers 1. Look at this, we computed it up here. This is the omega to the power 1, it's not identity. This is omega to the power 2, it's also is not identity. I'm sorry. So the only possibility for this to happen, or equivalently, the only possibility for this to happen is r being 0. But r being 0, given that the r is the remainder, is just simply saying that the k is a multiple of 3. So this equivalence now established. Right, so let me summarize now. What we realize with you is just omega to the power k equal 1 if and only if k is a multiple of 3. Good. Now we can look at the second expression here. So what we see now with you is that this expression equals 0 when, let me put it up here, this expression, it is equal 0 if k is not multiple of 3, because if k is not multiple of 3, then this is not true, which means this bracket is not 0, which means this bracket must be 0 in order to make this the whole product being 0. In order to make the whole product be 0. Now, what happens if k is multiple of 3? What happens? Well, we know that this happens. We know that the omega to the power k is 1, but what happens with this expression? Well, with this expression, if omega to the power k is 1, then we have 3 identities here. This is 1, this is 1, and this is 1. So the whole thing is just 3. And that's what we have for this expression in total. Yes. We see that this expression is either 0 or 3, depending on whether your k is multiple of 3 or whether your k is not multiple of 3. Now I think at this stage, when you see what happened with this expression, you probably realize what we should do with our binomial expansions, with all of these binomial expansions, in order to come up with the result we're after. Let me just scroll this page a little bit up. Let me scroll this page a little bit up. Good. Look what we're going to do. What we're going to do now, we're going to take all of these 3 expansions we constructed earlier and we're going to sum them up. Right. The left-hand side of the result will be trivially like so. 2 to the power n, which is the left-hand side of the first expression up here. 1 plus omega to the power n, that's the second expression up here. 1 plus omega square n, that's the third expression up here. But on the right-hand side, we have very interesting things happening. Look, for instance, these 3 coefficients together, they're identical. They just deliver 3 of such coefficients. That's nice, but if you look at these 3 coefficients, you will realize that 1 plus omega square This is this expression with k being 1. And k being 1 is not something which is multiple of 3, so this expression just 0. So the whole sum will just give you 0. The whole sum of these coefficients will just give you 0. The same story goes about these coefficients. Because these coefficients are mere, if you bring them together, and if you take this common coefficient, common factor c and 2 out of the brackets, the result inside the brackets will be 1 plus omega squared plus omega 4. And that's again this kind of expression with k being 2. And k being 2 is again something which is not multiple of 3. So the whole result is 0. Now here, of course, you get similar argument works for this column, for this 3. It's again this expression with k being 3, which is a multiple of 3. That's why in this position you got triple of the coefficient c and 3. You can go on with this fashion with all of the rest of the coefficients in your expansion. And I'll do this using the sigma notation. That's actually very clean sigma notation. If you bring these 3 sigma notations, if you add up these 3 sigma notations together, then you will have 1 plus omega k omega 2k, which is precisely this expression. And that's what is said here. If I bring this 3, you will end up with this. And we know that this bracket vanishes every time k is not multiple of 3. And every time k is multiple of 3, it is just number 3. So this whole thing becomes simply this. It's sum of all indices k from 0 to n, like so, but we only count those which are multiples of 3, and we take every binomial coefficient for such multiple of 3 and we triple it, we extra triple it. That's the whole thing. Look what we end up with. We end up that this left hand side here equal this right hand side. And this sum, this one, that's what we were looking for. That's what was asked in the initial question. The initial question asked for the sum of the binomial coefficients for every third binomial coefficient, or for every index k which is multiple of 3. So if I now denote this whole thing 3s, so this s is just symbolic abbreviation for this quantity we are looking for, then we just discovered with you that this s is just here. It's 1/3 of the left-hand side over here. Look what kind of miracle just happened. We were after the big, huge sigma sum, and with the help of complex numbers, we reduced this to the sum of 3. Yet, well, it's a complex numbers we have to compute up here, down here, but still, it's just a sum of 3 terms. Okay. Let's just finish this now. Recall that in the initial setup of the question we had n being multiple of 6. So let's just look at this carefully now. Let me just scroll this page a little bit further up. Let me scroll this page a little bit further up, like so. Right. Let's just look at the first bracket now. This bracket. 1 plus omega, the omega stayed up at the top. The value for the omega stayed up at the top, but probably I'll just copy it again for you. So omega was something like, no, it was negative, frat 1, 2, plus that was my omega. That's how we introduced the omega on the top of this screen. Now for such omega, if we compute this bracket, then 1 plus omega clearly just 1/2 plus root 3 on 2i. Now we need to compute this expression taken to the power n. Keeping in mind that n was the multiple of 6, so if I just reflect this in my computation here, so I have my 1 plus omega, and this is taken to the power 6m to the power n, which is multiple of 6. All we have to do, we have to analyze what's the 6th power of this 1 plus omega number. And that's something, again, I'll leave out of the brackets. It's something you can do, well, one way to do that using the binomial expansion and using the algebraic way we do arithmetic with complex numbers, but this is not the best way. The best way, of course, using the exponential form of complex numbers, and we will learn this. Some of you may know it, so you may probably check it right away, but if you don't, then we will check it a bit later. So I'll put here the dots for you to figure out how to compute that, or by the time we get to the exponential form of complex numbers, we will be able to do it together. So what I'm saying is this will be just 1, simply 1. Now, the same story goes about this bracket. If you take 1 omega square, 1 plus omega square, it will be just 1/2 take 1/3, because omega square, we computed it up there. Omega square was something like negative 1/2 negative something like this. So if you plus 1 it, that will be the result. If you take this to the power n, which you remember is a multiple of 6, so it's something like this. Again, all you have to do, you have to focus on this expression and the power 6 of it. Again, I'll skip some details here, but the exponential form of the complex number is the best here, and we will fill this gap later, unless you can fill it yourself. This will be 1, simply 1, and so this expression just simply 1. By the way, this is also 1. This is also 1. Perfect. So all we see now is just these two brackets are simply 1s. These two brackets are simply identities, which means that the result we're looking for is this. Look how nice and simple it became. Originally, your S was the sum here, sum of every third binomial coefficient for big n's, like a 60, for instance, which is multiple of 6. This will be a sum having 20 different terms, or for instance, for n equals 600, it will be the sum which has 200 different terms. And with the help of the complex numbers, with this very beautiful way we use the complex numbers here, we just reduce this expression to something like this. It's a very good example of usage of the complex numbers in relation to the question, which originally didn't have any mentioning of complex numbers at all.